Yeah, so good morning, everyone, once again, and welcome to this part of the course where we talk about power electronics in electric vehicles. So last week we went through the topic of onboard charging or offboard charging and the challenges from the powertrain side. Um, and today we will focus on the other side of the coin, so to say. So we will check charging infrastructure today, as promised. But before we start, I would like to hear from you once again. So please join the poll. You can also check it here. So we will start this one. So yeah, you can already start posting your comments there. And basically what I'm really curious is to see, what do you remember from last class? What was those points that were quite interesting for you, and that yeah, do you think are worth to remember? Yeah, for the ones who just joined, we are basically answering this question: what do you remember from last class? So we will give it 1 or 2 minutes so that I can know, yeah, which parts of the last class you remember. Yeah, bidirectionality, that's quite good. P2X. Okay, so let's close it there. So back to the presentation. Yeah, so last class we went through what some activities of energy bill, the concept of battery charging. So we went through this charging profiles of cars and how battery charging is conducted. So constant current, constant voltage, um, onboard chargers and offboard chargers. And we particularly talk a lot about this of onboard charger of an Audi e-tron or a Porsche Taycan. But today we will focus on the other side of the discussion. But before jumping into that, I would like to invite you all to this event. I think you have heard it from many sources. The Falling Walls Lab in Leuven. So it will be next week, next Thursday, March 28th at 8 p.m. And you perhaps you know it or you don't. Is basically a pitch competition. They need to present their ideas in 3 minutes. So quite interesting. And there we have actually one from our group, which is breaking the wall of electric cars, and more specifically the electric vehicle charging. So things that we mentioned or that I mentioned last week regarding onboard charging, bidirectionality, vehicle to grid, will be presented that day by Hans Wouters, one of our researchers. So if you are interested, you already have the slides in Toledo, so you can follow this QR or uh, the invitation that perhaps you already received via KU Leuven. And yeah, if you can join us, that would be quite great. More or less 15 presentations from many topics, not only engineering, and certainly not only electrical engineering, but way more other topics. In my opinion, it's quite good event to attend. So more than invited you all. Good. And then we jump into the topic of the main topic of these two sessions: charging infrastructure expansion versus powertrain technology advancement. And last week we did this poll, and you voted more or less 70 to 30%. So charging infrastructure expansion is still a big topic, and that's why we are dedicating time today towards that. But before jumping into how we can expand our charging infrastructure, it's also good to know why. And this, for instance, is a quite good assessment from IEA, International Energy Agency. The assessment that they did in Glasgow 21, like how we can really reduce the emissions, especially in CO2 equivalent, with different scenarios. So there you can see the 4 scenarios, like if we continue as it is today, if we do better policy, and if we, for instance, comply with the net zero by 2050, we will have these reductions. And there you can see, for instance, temperature rise if we don't do anything, or if our policies are quite weak, or if we implement the net zero in the coming years. And today I will be mentioning this a lot, like what happened with scenarios and with times when we talk, for instance, about demand and supply of electric vehicles. And I like a lot this slide from Derek van Herten in the Power Systems Group, talking about the role of the electrical networks, that electrification is the most efficient route to net zero, because of course is quite efficient. So electric vehicles, heat pumps in the Northwest Europe will mean 3 times more consumption, and we are already expecting like more than 1 million electric cars in Flanders by 2030 or even earlier. And also we will have more PV, like solar PV to become standard on each rooftop. Also, electrical networks are this possibility to connect cheap renewable energy sources to the local level, and also abundant renewable energy sources at remote sites. Also, for instance, thinking in offshore wind, for instance. Power electronics is a quite key technology there. We are already thinking in a 100% power electronics based power system, where you have seen those in the power electronic courses, in the electromobility courses, that we have more and more power electronics today. So energy efficiency is key. Last week, I discussed a lot about efficiency in onboard chargers, in converters, going into the details of certain topologies of converters. Once again, here we talk a lot about efficiency. So the best possible technology in terms of efficiency is electricity, and optimal use within the limits of the system is quite important. And there was this famous quote from Ronnie Bellman, that no grids, no party. So that's indeed quite important. And this one, perhaps you have seen it from The Economist some time ago, that there is a tendency to hug trees, but also we should hug pylons, because they are the ones actually that could take us to these net zero scenarios in the coming decades. Not only pylons, actually, we already foresee that with the tremendous amount of energy and power that we need in the future, we will not need pylons, we will need actually underground cables everywhere. But yeah, that's just an introduction of why the role of electrical networks is important when we talk about electric vehicle infrastructure. We have this change between the old and new power systems. You know that in previous decades we were having a pure dominant rotating machine driven system, and today we have a more power electronics driven power system. We have plenty of DC loads, we have plenty of DC sources, AC as well, so we need a power conversion in between always, or in most cases. We have these trends. So we have new technologies like renewables, battery storage, electric cars, electrolyzers, so power to molecules, so to say. And we have new concepts like high voltage DC, low voltage DC. You already have these talks from Johan, and also the concept of microgrids. The Panda one is one of the largest PV installations in China, and here in Europe we have these high voltage DC interconnectors, modular multi-level converters that are basically big converters to do transitions between AC and DC and to allow long distance transmission of power in DC. But yeah, this is quite well known by you. Just to close this part, just to mention, of course, that power electronics is everywhere. There is this analogy from Energyville connecting these four segments like mobility, buildings, industry, and electricity generation. And mobility, you know very well. Electrifications, we have vehicles with batteries. Molecules can also be used, like for instance, hydrogen for really long distance flights or even heavy duty vehicles. And in industry, we have more and more electrifications, molecules as well, steel and fertilizer production, chemical industry, and so on and so on. And in buildings, we are having a big renovation in buildings today. Again, electrification is key. Local production, energy storage, energy management, heat networks, all of those are key in those. And electricity generation, we need to, again, we will have way more people in the coming years. We need more energy to supply, for instance, electric transportation. So we need indeed to have more availability of power, and also molecules are also there. But the key point is more than each of these is actually the interconnections between them. Like for instance, we can have vehicle to home or vehicle to buildings. We can have, for instance, a solar generation. We can have vehicle to grid. I explained it last week. Hydrogen also, or in those points, for instance, in industry and electricity generation. And we have also the possibility to import hydrogen. Today, in all the predictions, is foreseen that Europe will not be able to generate all the hydrogen that is required. So we need actually to import hydrogen. Do also possibility to use hydrogen in transportation, heat there in buildings, in industry, and so on and so on. I think close it. So it's when we talk about charging infrastructure, we need to think about the losses in our system. In the previous part, we mentioned the importance of efficiency, and we will also talk about that. Today, we mentioned that more or less from all the electric power that is actually being generated today, or all the energy, in other words, 70% of that energy is actually processed with a power converter or a power electronics device at least once, and that's quite important, that part of at least once. So imagine all the energy that we have around 70% of all of that goes actually through a charger, through an inverter, through a power optimizer, a converter, an adapter, name it. So if we do the calculations, today we consume more or less 3,000 terawatt hour a year in Europe, and that means that the 70% of those 3,000 is actually 2,100 terawatt hour a year. And if we consider that most of the power electronics are actually quite efficient, if we check, for instance, PV inverters are extremely efficient. You remember from last class what are the efficiency numbers in, for instance, in battery charging. So let's say if we do a rough average of the efficiencies of all of these systems, 95% could be a good number. Peak consumption, when we take into account light loads, is actually way worse. But for this exercise, let's take 95%. And if we do, of course, the calculations, that means that we are actually losing 105 terawatt hours a year just in losses in the power conversion systems. And you can take this actually to the upcoming classes and also to the ones that you already had to see what does that mean. What does it mean 105 terawatt hours per year? How many households we can actually power with that energy? And even more, what is the cost of 105 terawatt hours a year? If we take into account, for instance, an electricity cost of 20 cents per kilowatt hour, which is a rough number if we take into account that in the use of electricity, there's actually way more. But in the point of, for instance, generation of electricity, 20 cents is perhaps too much. But if we do again a rough average, perhaps 20 cents per kilowatt hour is actually not a bad number. So if we take this 105 terawatt hour year, we put that 20 cents per kilowatt hour, we estimate more or less 21 billion euros of losses in power conversion systems. And there is actually the opportunity to see how we can actually solve that issue. And there the opportunity is if we work in these power conversion systems, like for instance, battery chargers, and if we increase the efficiency, for instance, by 1%, that means that we will actually be saving billions of euros, literally. The problem is that if you remember from the previous slides, we talk about at least once 70% of all the energy that goes through a power converter at least once, but it's actually never only one power converter in the system. If we, for instance, consider that offshore wind generated in the North Sea, that the energy coming there actually first goes through one of these MMCs, and MMC is basically these devices, like this very big. You can see actually here two persons, just for the sake of size comparisons. It's a huge device. Let me see, where was the slide? Yeah, here. So we can have one of these modular multi-level converters here on offshore and one onshore to do the conversion again to AC. Then in the power system, we can have many transformers, as you know, and one future device is the so-called solid-state transformers to reduce the use of copper and iron in these big 50 hertz transformers, and those are actually based on power converters. So we have the power systems full with with transformers, sorry, and then at home we have a battery charger, an EV charger, or it could be an EV charger in the city, and inside the car we can have actually a phone charger. So that's actually more conversion stages. So you can see from this simple exercise we can count basically 8 power converters here. So that figure of 4.2 billion euros, you really need to multiply it by many converters, because that's actually what is happening right now. And you can also do the same exercise, for instance, for losses, materials, CO2 footprint, lifetime. What about the lifetime of every single device in all of these converters? That's actually a big problem. And it's also a problem in the future. Like, for instance, if we look into 2050, where we have all of these goals of net zero by 2050, we can predict that by that time, perhaps we will have the 100% power electronics based power system. But let's imagine that is not fully perfect. 95% of all the energy that will be generated will go through a power converter at least once again. And by that time, if we look into the predictions, we are now more or less in a range of 3,000 terawatt hour per year. But in 2050, we will be in around 7,000 6,000 terawatt hour per year. And if we do the calculation, 95% of that, there will be more or less 6,400 terawatt hour per year. And again, if we do the exercise, but that time, of course, we can have higher efficiencies in our converters, but still we will be losing a lot in the range of hundreds of terawatt hours per year in losses. We do the same exercise. What will be the cost of that those losses in 2050? Perhaps in 2050 we will double the cost of 40 cents per kilowatt hour. So that means that actually more than 50 billion euros of losses just for this exercise. And we can also think what we can do at that time. For instance, increase the efficiency not by 1%, because that would be extremely hard at that time, but for instance by 0.5%. And there, once again, we will be saving tens of billions of euros if we consider only one single converter in this system. And it's not only about money, it's also about materials. Like if you check this 20% reduction of aluminum for instance, 2022, or 50% reduction of aluminum, or it could be the same in copper or steel in terms of or iron for magnetic components. We can also do that in terms of better use of materials. So yeah, that's the motivation, so to say, that if we do a better charging infrastructure with taking into account efficiency and high efficiency in particular, that will be actually good for our system. And there is the concept, of course, of smart grids. You have seen this a lot, like if we have different power sources like PV or molecules, hydrogen, or storage in terms of battery packs, that we can interconnect those to, for instance, a DC bus, either low voltage, medium voltage, or high voltage DC bus. And there we can actually have the interconnection to the grid. And today, I forgot to mention here the source. This is from State Grid China, this image. We can have transmission at different voltages. And in high voltage DC, we are actually talking today in 600 kilovolts DC in HVDC, and then we can have also high voltage AC transmission, and then distribution in medium voltage AC, and then low voltage AC. But in the future, we will have more integration of DC also in the medium voltage and low voltage. And here, making the link also to the talks of Johan Driessen regarding low voltage DC, that's also quite important, especially for electric vehicle chargers. Yeah, so that's basically the introduction of what type of energy do we need. Efficiency also quite important in the power system. The type of losses that we can have, the amount of money that we can save if we do a better energy conversion. And now we will jump more in detail in our topic. So what about, for instance, demand and supply of electric vehicles? So here I will be tackling this point from different angles. The first one is just for you to remember and the different type of charging connectors that we have available today. You know very well the ones that we use here in Europe. So we use these ISC types, the CCS, and the combined charging system, either for AC, or the CCS combo for DC, where we have the two points there for DC. But also, of course, there is the SAE types using in the US. Oh, sorry, the ones in China, the GVT standard the ones in Japan, and the GVT standard in China. And you have seen actually the news about the NACS connector, the North American charging system. which is basically the one of Tesla that many OEMs, many automakers, they are adopting nowadays in North America. This one has a big challenge, at least to be implemented in Europe, and is that although this is quite a compact connector, it only has two big lines there, and we can use it for AC and DC at the same time. It only allows a single phase connection in AC. And that's why we have actually that CCS type here in Europe, is to have the interconnection of the three lines or the three phases, L1, 2, and 3, and then a neutral point to allow three-phase connections. And that's basically the limitation. So when we talk about charging infrastructure, one of the first points to do is actually to select a proper charging connector. And here is the experience from Tesla, just for you to know. Of course, in North America, they are using the Tesla connector, and they are introducing it more and more for many automakers. The CCS is widely used in Europe and in part of Africa and also Asia. China, of course, they have their own, but there are a couple of countries, like for instance, Japan or South Korea, where they have both the Tesla and also the CCS connectors. So quite interesting experience as well. Thailand, Australia, New Zealand, they also have adopted the CCS connector. And the rest of the world is still a big puzzle, and that's actually the recommendation for many of these countries to actually select one, because if charging infrastructure moves forward and also we have more and more electric vehicles in these countries, without a standardized charging connector, that actually becomes a challenge for the countries, for the users, and also for the automakers. Let's see if we have, for instance, here in Europe, if we don't have any standardized charging connector, we would have cars from China using GVT or Teslas using the NACS, and it would have been a mess. Every user should have like many adapters, and that will be more costly to the users. Then the next point is how to encourage the adoption of electric vehicles. First step is to select a connector. Here in Europe, we already have the CCS, so that's okay. Then what is the next step towards that is to encourage more adoption of electric vehicles. And here I would like to mention the example of Germany. There are many good examples out there, but Germany has quite good practices, in my opinion. Like for instance, the investments in R&D, and that's also applicable to whole Europe and also to Belgium, where we have a tremendous amount of investments in R&D supported by, for instance, the European Commission with the Horizon Europe programs, for instance. So that actually encourage a lot the adoption, because we are researching on how to improve both the powertrain and the charging infrastructure. Also incentives. So we have seen incentives everywhere, also here in Belgium, like several years ago with tax incentives, not anymore, but still, and also, for instance, towards company cars as we know it. In Germany, they did also these reductions in road toll for trucks. Here in Belgium, we don't have tolls, but for instance, in France or some other countries that they use, that could be also a good way to promote electric vehicles, to reduce those toll fees that, for instance, to zero for electric vehicles until certain years, like for instance here up to for 2040. Also to encourage the transnational networks. So not only looking inside the country, but also looking outside with interconnection to other countries. And this one is quite unpopular, but in my opinion, quite effective, and is actually to discourage the use of the internal combustion engine vehicles by means of more taxes. If we have, for instance, today diesel and gasoline cars, one way to promote the adoption of electric vehicles is actually that those cars will be more expensive, at least until to promote, at least, like for instance here the second one, to reduce the price delta between electric vehicles and ICEs. And there is already a good plan by 2028 for most of the automakers to produce actually affordable electric vehicles. And then is quite good in order to reduce that delta. So yeah, lessons learned from this exercise. I was doing this exercise from last year. It's actually from those countries that they have not selected a standardized connector to do so. Also to check the location of superchargers, like for instance these Tesla superchargers or any other fast chargers, 50 kilowatts to 350 kilowatts and more. Like if you see the plans of Tesla is actually to have superchargers even in the range of 700, 800 kilowatts of rated power. Also to determine what will be that power per off-board charger. Like today, most of the cars, they don't allow extremely fast charging, like higher than 250 kilowatts or even higher than 100 kilowatts. So that's important to check what will be the perfect or a suitable power per off-board charger in order to use the grid in a better way. Governmental support, I already mentioned this in the previous slide, like tax incentives and also specific financial policies. And also to check, for instance, in highways and national roads, what will be a proper a number of chargers, or especially DC chargers or off-board chargers per 100 kilometers, for instance. We can also talk about a good ratio between electric vehicles and chargers, and also it's important to talk about a good ratio of chargers per 100 kilometers of roads. Yeah, and we will talk about that in a minute. So then, if we know that we need connectors, we need policies, then how to estimate the power demand when we have quite many electric vehicles in our cities, in our provinces, in our countries. So the first thing is to check, for instance, what are those sprayways or highways network plannings, like if they are going to be expanded or then the amount of charges that we will have there also in cities, and to check what is the projected electric vehicle fleet size in a country or in a region, and also to check what will be those anticipated future traffic volumes. And when we take into account those, we will be able to predict what will be the future energy or electricity demand that we will have in a country. So yeah, we can also translate that into this. We can have, for instance, as an input, the road and traffic status, forecasting studies, the development plans of the countries. And on the other hand, we can have actually models of electric cars. That's more tricky, but we will come to that in a minute. We can, with those models, we can estimate the energy consumption per car. And with these three ones here in blue, we can also estimate what will be the number of vehicles that we will have by certain time. And with that, we can calculate more or less what will be the power demand in this specific scenario. In other hands, if you would like to see it in equations, that's more or less the energy in a year, depending on the power per car and the numbers of cars, and then we can have more or less the maximum power that we will require. Also, we can, one thing is that the demand, the other one is the supply, the power supply procedure. So we can have also as input the estimated electric vehicle fleet size and the total power demand from the previous exercise. And with that, we can calculate what will be the future electricity supply that we need in the region. Just to put it also again in a kind of like a flow chart. So we have the power demand, the number of electric vehicles, when we can combine those to estimate what will be the suitable charging station configurations. And then we can have, for instance, power supply parameters and also the standard power supply parameters that we can have in a country, or we can compare and then we can estimate optimal configurations. So just to give you an example, we can have different types of segments, so to say, car segments or vehicle segments. Like for instance, small passenger cars, also for instance, buses, heavy duty vehicles, and so on. We can have all sorts of vehicles. When we talk about electric vehicle infrastructure, is not only for passenger cars, it's also for heavy duty, it's also really for light electric vehicles, like for instance, bicycles, motorcycles, three-wheelers, cargo bikes, and so on. And here is just an example of how to estimate the energy consumption of a vehicle. We use the so-called standardized driving cycles. So with those driving cycles, you can see, for instance, some examples like the WLTC, quite used today, Worldwide Harmonized Light Vehicle Test Cycle, or also the so-called new European driving cycle that is not new anymore, it's quite old actually. There are also the ones in in the US, like the EPA or the FDP driving cycles. So different driving cycles. What is a driving cycle is basically a set of conditions of a speed versus time. So we can have, for instance, driving cycles taking into account highways, taking into account only city driving, and so on and so on. And here, for instance, you can see different speeds, top speeds. Like for instance, the new European driving cycle is considering, for instance, a highway speed, distance, and times. And taking into account those driving cycles, we can estimate more or less what will be the energy consumption of each of these segments, so the passenger car, the bus, the truck, and so on. When you go and buy a car, you will see actually in the information that they say, like the energy consumption, this number, for instance, in watt hours per kilometer, or liters of gasoline or diesel per certain kilometers, and that's based on these standardized driving cycles. Those are a little bit far from reality, because when you consider actually real driving cycles, the consumption is higher. But nevertheless, it's good to have a fair comparison among cars, and that's why we use these standardized driving cycles. Look at these numbers, like 168 watt hours per kilometer, 234 watt hours per kilometer. Maybe to you, to see if you're still awake. Do you know what is the well, without looking into the slides, of course, because the answer is in the next slide. What is the car with the lowest energy consumption, electrically speaking? Can you tell what will be a good number in comparison to these ones, 168 or 234? What will be a good number of energy consumption in a car? Can you type it in the chat, or can you just mention it orally? You still there? Victoria, Diego, Tun.
Yeah, I guess 150.
150 watt hours per kilometer. Any other number? Ton, Helen? Okay, so yeah, last year, well, sorry, 2 years ago in 2022, there was this record by the Mercedes Vision, the EQX, and there was this very big highlights of the car driving over 1,000 kilometers on a single charge, and then when you do the calculation, actually the car had this consumption of 87 watt hours per kilometer, so extremely low. When you go and consider this versus many other cars, I have this long list, for instance, going from the Lightyear until more heavy cars like these Mercedes SUVs or the Audi e-tron. The Audi e-tron is a quite heavy car. And there you can see more or less the average of all of these cars is around 200 watt hours per kilometer. And there you can see also quite a big change among cars in terms of energy consumption, like going from 100 until 300 or so. So that means actually that we can have different energy consumptions depending on the car. So it's not like if you are driving electric, you're already quite efficient. No, it depends pretty much on how you drive and also the type of car that you are using. If you use this Mercedes EQX versus this EQV, the consumption is way different. And then you can do scenarios of development, like if you have, for instance, a slow market uptake or a net zero emission scenario, or even an accelerated net zero scenario, you can have different percentages, and then you can calculate the possible EV fleet size, and then you can run the exercises that I already mentioned before, and then you can more or less estimate what will be the number of electric vehicles by certain time and feed the model, and then you can have more or less the predicted power. Then the point that I was mentioning in terms of EV number of electric cars per 100 kilometers or number of EV charges per 100 kilometers, also we can do the same in numbers of chargers per electric vehicles. So there are these comparisons. I think they are very well known of what is actually an ideal ratio of EVs per number of chargers. So in blue, for instance, is the number of electric cars per charging point. Like for instance, here you can see that the best is actually South Korea. South Korea is setting really high standards in terms of electric vehicle infrastructure. And also the point, these red dots there is actually related to the charging infrastructure, how much power is actually installed versus the amount of electric cars that there is in a country. And also South Korea in that regard is actually quite high, with powers above 6 kilowatts per electric vehicle. There are some others with quite small numbers. These numbers quite difficult to digest those, but is maybe I can refer it already here. It's exactly the same curve. Looking into electric vehicles over electric chargers, and also checking the power per electric vehicle that is already installed. The International Energy Agency recommends 10 electric vehicles per charger, so a ratio of 1 to 10, and more or less 2.4 kilowatts of power available per electric vehicle. At this moment, Belgium has more or less a ratio of 13 to 1, at least when this information was taken, and 1 kilowatt per electric vehicle. That means that we are not that bad in the number of chargers, although we need way more. But still, in terms of power, we need way more power per electric vehicle. That's basically the point. And there, everything goes to the point of where actually is the bottleneck of this electric vehicle demand. If it's really in the transmission, or if it's really in the distribution side, and the answer is actually the low voltage distribution grid. When we have these interconnections, like I mentioned before, going from high voltage, medium voltage, and low voltage, I really like this analogy that we use in energy wheel with the electrical network research line. That basically, when we talk about low voltage distribution grid, it looks more or less like this. There is basically or literally no equal low voltage line in the country. So every single line is actually different powers, different extension, different loads. So it's quite hard actually to manage that conditions. And here is just once again, if we are having quite a lot of electric vehicles, quite a lot of PV batteries and so on, if we look into the plans and how actually our cities look like in terms of the loading percentage, meaning that if we have a line and the line has a certain rated power or capacity in the line, today more of those are actually not that loaded. But in the future, if we have way more and more battery chargers in our cities, those lines will be easily loaded in the future. So we need more low voltage distribution lines, and we need actually more redundancy there, and we need to increase the power in those lines, and that's actually a great challenge. So with that, I will jump then to the topic of charging infrastructure, how to achieve that. I will just look into the time. We have already 1 hour here, so I think we will be okay. Yeah, and I will be using material from one of our PhD researchers, called Mohamed Jasko, that Johan and we are supervising. So yeah, this is the same project that I mentioned last time. So is within the power electronics research team, the design and performance evaluation of EV charging infrastructure or charging architectures. So what we are doing is looking into the vehicle, like what type of vehicles we can have, what type of chargers we have there, and let me open this. Sorry. Yeah. And what type of efficiency we have in the onboard charger, and also if we have PV, then what type of forecasting of PV we can have, generation of PV, and there we look into what will be the optimal charging infrastructure, if we use AC or if we use DC, how many chargers, the powers per charger, and so on and so on. So one question that we need to ask there is what is the optimal charger location? We already mentioned last time, like there is these two concepts of off-board and on-board. And on-board we cannot do much, but off-board we can, meaning that we can, if we have a battery, we can have different types of converters. Like if we use first an AC to DC and then a DC to DC, or if we go directly from AC to DC isolated here, or if we use, for instance, a transformer, and we go, for instance, here in low voltage instead of going, for instance, here medium voltage. or the conventional one. So there are plenty of options there where we locate the offboard charger. Like for instance, this is the conventional AC, the conventional AC example where we have the transmission. Then we can have in high voltage to medium voltage, and then we can transform it into low voltage AC, and then we can distribute it among many charging points. But for instance, we can have also the case of DC, where we have the AC source and also possibly PV, and there we can have coupling transformers, and then here an AC to DC converter, and from that we can distribute in DC towards all those points. And those are actually these. There are plenty, but this is just one example. This power store concept from Hitachi ABB, where it involves also a storage, like for instance from batteries, and then we can distribute it among DC. So that's one example. So taking into account this, Jasko has been working in this, like in one project coordinated by Johan called Hume, where we the objective was to evaluate, for instance, what is the effect of having an AC bus architecture, a relatively low power. The conclusions were that, for instance, the advantage is that in terms of protection, AC is already quite mature. There is already quite very well known AC protection systems, so AC breakers that are easy because, as you know, AC has a zero crossing point and it's really easy to detect faults. Standardized metering is there. However, control is complex. We need more conversion stages because we need to have closer to the car many AC to DC conversions, and we can have also power quality issues. While, for instance, a DC architecture, we can have actually higher power there. We can transport more power per sectional area of the wires. You know, it's that with AC we are actually wasting material because due to the skin effect, we don't use the central parts of the wires. So in this architecture, the DC based architecture, we can have a simpler control, less conversion stages because we can go directly from DC to DC. We don't need everywhere AC to DC conversion, and of course we can have less power quality issues. However, we face the challenges of protection because DC breakers are not mature as AC breakers. There are no standardized metering. We can have quite a capacitive nature in the system. So yeah, some challenges. And perhaps we can actually have a combined architecture where we can have an AC bus and a DC bus, and we can interconnect many loads there. So a big question actually today is what is the most suitable architecture, for instance, for public charging or even for home charging or for fast charging. Those are there. So when it comes to charging infrastructure, it's not like there is a single truth. Is actually depending on each scenario, each particular conditions, and so on and so on. So this is Jasko's project. We are looking into the comparison of charging in architectures, looking, for instance, in the efficiency in the power conversion, looking into single and three-phase systems. From the talk of Johan, you know that there are different types of low voltage DC architectures, if it's bipolar, if it's unipolar. What is the cost and benefit, for instance, the total cost of ownership of these systems, and looking, for instance, into use cases like the ones here. We talk a lot, of course, about efficiency. So we do efficiency analysis, looking into data sets, looking into experimental work. So we are actually conducting measurements. Last week, I showed you some examples of efficiency measurements. So that's there. And also we involve, for instance, storage, local storage, like what is the optimal battery operation, looking into age and models, how to charge those batteries, peak shaving, for instance, and so on. So here, just yeah, this is just one example from the quantifying degradation of taking into account electric vehicle charging and the average capacity versus time. So looking how those degrade over time. So just some examples, like for instance, charging infrastructure, having for instance the 400 volts, 50 hertz, and all the charging or the conversion stages that we need in there. Once again, taking into account these when we talk about, for instance, efficiency and cost. What about, for instance, battery integration? Like if we have this PV self-consumption as well, how to actually to manage the energy flows inside this architecture? What about the costs of such system? What will be the electricity price that we will charge these cars? So those questions are actually the ones that we are tackling in Jasco's project. Yeah, so we can go from, again, the AC charging architectures or the pure DC charging, having different scenarios where we can have actually a PV directly connected to the AC or PV directly connected to the DC bus. What are the consequences of those changes? What voltages, what powers, if it's bipolar, monopolar DC, those points really there. Yeah, those points where we can actually have local PV and more centralized batteries, centralized storage, or combine architectures where we have, for instance, charging, DC charging in certain points, AC charging in some others, and so on and so on. And here is also important to take into account, for instance, what about bidirectionality? What about if these cars can also supply energy to these architectures? So that's also that we will consider in the future. Also, the topics of single to multiple power sources, AC to DC, what about multi-port converters? And all of these architectures are actually being designed, for instance, for kilowatt levels. So in low voltage, in low power, 11 kilowatts, in high power, 50 to 250 or 350 kilowatts. But what about megawatt power levels? And that's actually the challenge. The next point is actually how to do the battery charging in a proper way. We can have different architectures, but then is how to really put that into consideration when we are going to charge the batteries. So the basic charging scenario is that, for instance, we connect, for instance, the car at 8 a.m. We use full power, for instance, for AC charging until we disconnect the car. But we can also check, for instance, if we have more time, we can actually reduce the power per charging, and actually we can distribute, for instance, this 10 kilowatt hours during the day, or even better, if we are able to play with the charging strategy, we can have some times where we can have full charging and some others where we can actually derate the charging. And we can have, for instance, times where we can charge full one car and some others where we can actually shift the charging of other cars. And that's yeah, one of the strategies how to play with, for instance, charging in there when we have different cars. So that's the basic one. We can also have a control charging strategy, like for instance, if we have unidirectional control, or even if we have vehicle to X, or if we have, for instance, into account dynamic pricing with automated control, there we can check during the day and at different charging powers if we charge different vehicles, or if we have, for instance, an adaptive charging, we can limit all of those and charge in a smart way. So you know where I'm going, of course, is the concept of a smart charging. So several studies over many several years, and actually we are doing a smart charging already in Energyville. So if you are interested in these topics, just let us know, because we are working intensively in that. And there you can see different scenarios of penetration of electric vehicles. And there we can have that if we don't have any control charging, yeah, there could be a certain curtailment or certain restriction of charging, and we can have increase of peak loads, of course. But if we implement smart charging, like the ones that I already mentioned, we can actually have better metrics in those points. Take into account this point of smart charging, because you already saw it last week, but it's quite important because we mention a lot smart charging, because it's an easy way to not saturate the charging infrastructure. But we need to take into account also what happens if we have, for instance, these conditions, or even better, these conditions for the car, for the powertrain. So, and there is this point. So charging efficiency is quite important during smart charging. You know that we can have the wall box, and then inside this, we went through this in detail last week. And we have an onboard charger, and that onboard charger is full of electronics, so power converters. So you know very well that the charging efficiency is actually not that good at low or light loads, low power, and we can have actually different points during the day of efficiency. In other words, is basically this slide that I mentioned it last week. Efficiency is actually quite high when we are at rated conditions, but for instance, when we land in light loads, like for instance, smart charging using, for instance, solar, we actually face this low efficiency profile. That's something that we need to consider when we are doing smart charging. Then what about high power charging? Because all of these scenarios are really for low power or relatively low power, and in the range of tens and hundreds of kilowatts. When it goes to high power, is actually a big challenge today. How to supply, for instance, megawatt charging. Like for instance, we have a full dedicated line only to supply few buses or few trucks. That's also a big problem. So there is already the concept of the MCS standards, so megawatt charging standards, and Johan is also quite busy with that, how to charge a truck, how to charge buses. And it's a new standard, like for instance, the CCS today is up to 350, 75 kilowatts. The previous CCS went until 130 kilowatts. And in the future, so we have more and more. I already mentioned, for instance, the one of Tesla, that is in the range of 700, 800 kilowatts, the next generation of supercharger. So yeah, thinking in megawatt is also quite important when we talk about charging infrastructure. So there are some concepts, like for instance, this one from ABB, where we can have like a regular charger for a car, and also we can have this catenary or this pantograph configurations where we can charge also at the megawatt level these buses. Or even in the future, we can think more and more in the concept of wireless charging in the megawatt range. Good. The last part of this is actually a good news. That is that when we have different charging behaviors, like we can charge at overnight, and we can also charge during valley hours, so to say. So if we are at home, for instance, we are charging basically when we reach home, so at evening. But at work, for instance, in Energyville, we charge during the day between 8 to 5 or 8 to 6. So we are actually consuming a lot of energy from the grid during the day. And for instance, public fast charging is actually during the whole day, also for instance in the early mornings and so on. So something that is happening is actually that the consumption is being spread. So it's not only localized and centralized only during the peak of demand of the rest of the loads, like the conventional system. That is, the peaks actually happen in the morning, and then in the evening we can actually more or less distribute the consumption of electric vehicles during the day. And that's actually good, because it's not like we will increase just the peak in a worse condition. Just to finalize, these are the last parts of my presentation. Is that the concept of like these new concepts? I happen to know this company called EV, which is offering this concept of blockchain. Like for instance, here you can see the rapid charging system for fleet operators. You can get 150 kilowatt DC charging in every space, and it's kind of like a cost effective. You don't pay the capex, so that's the business model, and it's kind of like a scalable model. So kind of like a homework. We will discuss this perhaps at the end during the exam. Please go and check this website and reflect on this particular scenario. Yeah, perhaps you can give us some feedback and let us know what you think about these new concepts, for instance. Good. So that's more or less kind of like at the end of my presentation. You remember this question that I posed last week, like what is the charging, what to prioritize, charging infrastructure expansion or powertrain technology, and last week you gave your comments. So once again, I would like to ask you this after these two sessions. So if I go once again to the same question, let me see. So please answer this once again. Which should you or should we prioritize for EV adoption after all these discussions that we had on charging infrastructure and powertrain technologies? Also, it's a good way to measure if you are really paying attention or not. Okay, so it's almost 12. So the last part is this. I took this one from a presentation in APEC. Quite nice to compare, for instance, the Apollo 13 movie, where they mention like a power is everything, and we can actually mention that it's not only power, so efficiency is also everything. So yeah, that's the main takeaway message that I would like to give you from these two sessions. So once again, thanks for your attention, especially the one that is paying attention at this very moment. Not sure if you have any questions, so just let me know. If not, we can close the session here. Yeah, so Victoria is asking, what are the opportunities for a student in energy will to work with these topics? Now it's not only for PhDs, we do have quite plenty of opportunities and many options. Like we have the student jobs, we have the master thesis, we have cooperation, we have these student programs like the Technovation Hub, where we have actually students working in this battery charging or charging infrastructure and the smart charging strategies. So there are plenty. So just send us an email if you're interested in these things, because it's not only for PhDs. We have plenty of work, so to say. Yeah. You can open your mic, Victoria, if you want. Yeah, thank you. Okay, so if you don't have any other question, have a great day, and yeah, see you next time, perhaps at the end of the semester with the exam period.